So I'll go ahead and introduce myself. My name is Tony Muscatello. I'm, as I said this morning, I'm an R&D chemist at the Kennedy Space Center, and I have my NASA hat on today. I have my NASA pin on right now. So this is a reviewed talk by NASA, and well, let's get started. And I'm going to talk to you about the carbothermal reduction demonstration that was held on Mauna back in January and February in Hawaii. So just briefly the outline, we'll go through a little background information and results and so forth. So just a quick definition, what is carbothermal reduction? Well, if you're not a specialist, you might not know what that is, but basically the idea is to extract oxygen from regolith by melting the regolith first, running methane over the regolith. The methane breaks down into carbon and hydrogen, and the hydrogen goes off, may reduce a little iron oxide, and then the carbon reacts with both iron oxides and silicon oxides to make carbon monoxide, which bubbles off, takes the oxygen with it, and leaves behind iron metal and silicon metal. And I'll go into more detail in a moment. So if you look at a simulant like JSC1A, it's 28% oxygen that can be extracted from this process. Another process you may have heard of is hydrogen reduction. That can only get like 1 or 2% oxygen. And so we can use this really any location. The moon, Mars, asteroids, moons of Mars. You could really process that regolith no matter where you are. And so here's a little more of the chemistry. You've got to get it hot so it melts. And then you take the carbon monoxide and combine that with hydrogen to remake your methane, which will recycle through the system. This is the same process as the Sabatier reaction, except it's with carbon monoxide instead of carbon dioxide, but you use the same catalyst in similar conditions. And then you get water. So you electrolyze the water, you get hydrogen, which goes back into making the methane, and then your oxygen, and for a net reaction of metal oxide is reduced to metal and oxygen, which you want. So next step. So what are these steps? And I just told you about all of those, and you electrolyze the water. And so this is just another graphic. I'm a chemist, I like showing equations, but this is my co-author, I should have said, is Robert Gustafson. He's an engineer at Orbitech Corporation who actually did testing of this equipment. I only supplied the second A in NASA, which was administration, and through being a contracting officer, technical representative, I have a little technical input there, so I have a little bit of ownership. But I thought you all might be interested in seeing this. Next step, please. And here's another slide that's too complicated to go through everything. But the idea behind this demonstration was to take, starting with regolith, you extract the oxygen from it. You send the oxygen you extract the oxygen, you make water, you send water to a separate electrolysis unit, and that's shown over here. And then that electrolysis unit makes hydrogen, sends that back to make more methane. The oxygen goes on to be stored as liquid oxygen, and then you take that liquid oxygen and send it to a little rocket engine, and you burn that use the oxygen to burn methane, which was brought separately. And then that was all, the hydrogen and oxygen from the electrolyzer were also used to run a fuel cell, which at some points we use that power to run a carbothermal reduction system. So we have a closed loop system, and the idea is to go from dust to thrust, as you would on the moon or Mars or whatever. So this is a photograph of the carbothermal reduction module as built by Orbitech. And there's automated filling of the hopper and so forth, gas handling systems and so forth and so on. You can run it through a laptop, through an HTTP interface. And this design was sized to, when it was fully built out, to make 1 metric ton of oxygen a year on the moon. Right now, it's only operating at like 1/10 scale because we need more energy, and it would need some modifications. But anyway, the reaction occurs in here, and there's a connection here where we bring solar energy in. and then all the chemistry and so forth that is done out here. Here's a hopper that takes the regolith and sends it into the system, and an internal hopper as well. Next slide, please. This system has been adapted to be used with a solar concentrator. This was built by Takashi Nakamura at PSI in California. And the idea is we have 7 of these parabolic dishes that reflect sunlight up to a secondary mirror, and then that secondary mirror reflects light down into this light gathering area into fiber optics, and then these cables that you see down here all get gathered together into a single intense beam of light which is shined upon the regolith to melt. And we can get up to around 800 watts, 800 watts of energy delivered for one of these. This whole unit. Next slide, please. So testing at Orbitech showed that they can get up to around 10% oxygen extraction with both lunar simulant and tephra. This shows that fuming comes off, so we have to have a gas blowing that away so it doesn't contaminate our optics. And let's see, and it shows this some of the molten glass that has been melted and solidified in the system here, and then it's, a couple of 9-inch crack across, and this is a chunk of that glass after it's been processed. Next slide, please. I mentioned this body A reaction. It's also called a methane reformation reactor. Pacific Northwest Laboratories has built a unit that was tested, and then Orbitech built its own version. Turns out we used the Orbitech version because we ran into some issues with this one. This is a micro-channel reactor. It uses very small amounts of catalyst to be very lightweight, but it's also very touchy because carbon monoxide can disproportionate into carbon, and carbon dioxide, the carbon will clog up your reactor. This one, it runs at a lower temperature, and so the carbon monoxide does not disproportionate, but it's still fairly efficient. Next slide, please. So here's a photograph of the field demonstration site at the 9,000-foot level of Mauna Kea. There's various tents that were there to house the people and the equipment and hardware. This is our mission patch. So, like I said, we were there in January and February this year. We'd also been there back in November of 2008, and I spoke last year about the results of that test for a lunar volatiles mission that we may be getting. Let's see. Next slide, please. And so we go to Hawaii, and where do we go? We go to a place that's cold at night and in the morning. They actually measured the temperature around 24 degrees one morning. There's frost on the ground. This was not a cake job. It's in Hawaii, but not the most scenic. Well, it's scenic. It's beautiful. It looks like the moon or Mars in some places, but it's some way Mars. It gets cold. Anyway, there's frost on the dishes and so forth. You have to cover your laptops with plastic because the wind blows and the dust goes everywhere. And some fog would roll in every now and then. We had some dust storms and sandstorms. Next time. And here's a top view of that same site. We have this valley we operated in, and then there's some cinder cones nearby. And so this area is filled with this tephra, which is volcanic ash. Next slide, please. And there's a closer up view of it. It looks something like the moon or Mars, as I said, on this level of Mauna Kea. Next slide, please. And here's just another view of the hardware. There's the solar collector again, fuel cell. Canadians built load haul dumpers to deliver the tephra. There's the carbothermal system. Hydride storage was also there, as you mentioned before. Here's the thruster and electrolysis. Next slide, please. Oh, and now can you go to the video? Yeah. Exit out of the presentation. I haven't tried integrating the two. So yeah, just go ahead and run that and show you a little bit. Oh my goodness.
Yeah, that's good old Bill.
Oh, there you go. If you could look blow that up, and there you go. And Chris, that's okay, it's right. Okay, so, yeah, here's some stills and video. Here's another view of the test site. And that's the load haul dumper delivering the regolith into the hopper. We also tested a pneumatic lift that would bring the material in. Let's see. Loading it into the system. There's a little video of the Tetra being augered inside the reactor. And then the solar energy module and the thermal system. More photographs there.
Did you say that that module produces enough heat to melt that regularly?
Well, in that one spot, yes.
In that one?
Absolutely. Here's how it does it. This is what it looks like. Now, this is 2 millimeters across down here in that reticle. So this is all blown up, but you can see as soon as you turn on that sunlight, it delivers it to this area, and the material starts melting and agglomerating and moving around.
Is that enough the silicon that's melting?
Well, it's the
Silicon
the whole thing it melts. So that all of that, and there's a reflection of the light coming in there.
I would,
And this is what it looks like when the methane is running and the carbon is reacting in the next. So you're reacting. And so you see the surface moving around, and these little beads are iron metal beads that have accumulated over time as the iron oxides have been reduced and accumulate. And then it's bubbling with the carbon monoxide that's coming out of the system. And so we collected some water here, and that was electrolyzed and recycled, as I mentioned. There's an example, this claw, this Wolverine claw comes along and picks up the glass after it's finished, dumps it down a chute, and that opens up and drops the processed material wherever you want, on the ground, whatever. We did do an experiment where we collected it with the load haul dumper to haul it, or if you want to use it for something to get out of it. And there's what it looks like after you've processed it. So, great, so if we can get back to the presentation.
So this is very much a batch process.
Well, yeah, it is. Although you can build up enough gases so that you can just keep the gas chemistry part running fairly continuously in the electrolysis once you get some backup. You can store that. And then so you start running, and then while you're moving stuff around.
you recreate the methane, right?
Yeah, you recycle that back through the system.
How do you capture, how do you change, or what is the scale of all of this in terms of capturing the gas and storing?
About, tanks so big, so like I said, this is for a metric ton a year.
Have you looked at trying to magnetically separate iron and just processing the iron?
We've thought about it, but we haven't done it yet. But
Because that would be a much lower energy.
Yeah, I might have to go back.
But you could just do it directly
Oh,
with
sure, I'll try
hydrogen.
these. Try these.
how does there you go? Go and open.
It's not like working on it.
Sorry about that.
Yeah, that's okay.
Down here, some
Scan down there.
Especially.
Zip through. Just a few more, I think.
Is all of the energy provided by that solar plant?
Well, the energy to melt, not the electricity that you need to run the pumps and things and stuff.
Right.
Okay, so here's the results. We considered ourselves to be successful. We got fortunate that the weather cleared up after looking bad the first day we did a test run. And so we had a total of, I think it was like 17 runs. A couple of them were turned over, to testing for loss power spectroscopy to see what happened to the iron chemistry and so forth. And there's some of the water, as I mentioned, and some more test results. Next slide, please. And here's an unreadable graph. I had another version where I had this highlighted, I think. But anyway, the total summary of that is that we had a 10% oxygen yield on most of these runs, Now, this tephra was dried somewhat, but not totally, so some water would come off during